Hello, everybody. Welcome to our next section of nuclear physics. Today's topic is going to be on fission. Uh, we've heard of fission before. Most people know that fission is the splitting of the atom. We're going to go in a little detail about that, and then we're also going to talk about the nuclear mass defect, some of the isotopes they use to do fission. We're going to talk a little bit about critical mass, and we're going to talk about how they made the atomic bombs used in World War II. And then we're also going to talk about nuclear reactors and how they work. And at the end, we have some questions that you'll have to answer. So, as we do these, and you can do this in Google Docs, but copy the original thing that I send you into your own Google Docs, make a copy of it, and then you can just write the notes or type the notes as we talk. Some of you guys have a pencils that you can write on these too. That's fine too if you want to do it that way. And some people just like to write the notes out, print it off and then write on it. That's fine too. But we want the notes and the questions at the end completed when you're done. So make sure that you take the notes with me. Don't just answer those questions and Google them. We want you to try to learn this as we go. So make sure that you follow along and write the notes as I give them to you. Okay, so first of all, nuclear mass defect. Nuclear mass defect is what a lot of people wait their whole lives to hear about in science class because it is the M of equals mc squared. Now, everybody in this class probably already knows that E stands for energy. And we know that M stands for mass. And we know that C is the speed of light. And Einstein, as he's punching through equations and trying to understand how the universe works and how light works, he comes up with this really simplified equation where he combined different physics equations together and came up with this simple thing. And for the most part, everybody knows that simple is usually right? If it seems too easy, that's the right way. And he came up with this equation, and this is the basis of nuclear energy in all things that we're talking about in this section. But what is that mass? That mass is what we call the nuclear mass defect. All right, now let me put this in terms that, like in class, I usually go by the mass of all the people in class. So we'll say we have 10 people in class. Oh my gosh, I should have said 5. I'll change it to 5. So we have 5 people in class, okay, small class. And each of those people stand on the scales individually. And this guy here, he weighs 100. And this guy here, he weighs 110. And this guy here weighs 90. And this guy here weighs 100. You see what I'm trying to do here? And this other guy weighs 100. So we find the average mass, right? And we see that, the mass of all these people is about 100 per person. That's individually. Now we put them on the scales. And when we put them on the scales, we put them on all together. So we put them all on a big scales together. And on this scales, it's not a time for social distancing here because we're all standing on scales together. And so they all stand on the scales together. And we take a new weight. And the weight comes up to, and you're going to guess 500, right? No. The weight didn't come up as 500. The weight only comes up as, we'll say, I'm just going to make up a number here, 490. Right? Oh my gosh. Did I weigh them wrong originally? No. Did I weigh them wrong at the end? No. The nuclear mass defect is talking about when a nucleus is together. This is when a nucleus of an atom is together. And we're talking about the neutrons and the protons, right? Are all jammed together. They weigh less than they're supposed to weigh. They have a smaller mass than they have when they're individual pieces parts, right? And what that is called is the nuclear mass defect. The nuclear mass doesn't add up exactly what it's supposed to be. When the neutrons and protons are together, somehow when they join together, they lose mass. Okay? And that loss of mass right there, that mass times the speed of light is what's going to produce the energy of these nuclear reactors. Okay, so definition: nuclear mass defect, the mass of the nucleus is less than it is supposed to be. Right? Does that make sense? I hope that makes sense in common terms there. So the mass of the nucleus is less than it's supposed to be, and that lost mass is what we think of as the energy. Okay, so let's talk about our first reaction, and that is fission. And fission is the splitting of the atom. Right? It's the splitting of the atom, and it goes through a little reaction, kind of. What happens is, I have that in green. That shouldn't be in green. That should be in purple. Right? Make it look more like what it's supposed to be. There we go. So they fire a neutron into a nucleus, a large nucleus. This is uranium-235, very fissile material. And that neutron gets absorbed for a second, and it kind of morphs the nucleus, and it kind of stretches it out. Now, remember what we have. Inside that nucleus, we have a ratio of protons to neutrons, right? Those neutrons are trying to spread out. Oops, I can't write today. Trying to spread the nucleus, right? And what that does is that reduces, it's supposed to be in either, reduces, I'm going to change this font, reduces the electromagnetic force, right? Because remember, those protons are pushing against each other. They're trying to push each other apart. The neutrons stretch it out, so there's more space there, and there's less force pressing apart. All right. So when these ratios become disturbed or changed, the nucleus becomes unstable, and they're forcing this to happen, right? And it causes this thing to split into two pieces. Okay. Now those two pieces don't have to be the two pieces shown there. They just two medium-sized pieces. And then usually they spit out a few extra neutrons too, right? They're smaller nucleuses. They don't need as many neutrons, right? Because that's what those neutrons do. They keep the large nucleuses spread apart. Smaller nucleuses need a smaller ratio. Okay, so so that is what fission is. Now, the fissile material that is used is uranium-235. Okay, and this is an isotope of uranium, and it has 92 protons, and it has 143 neutrons, and it goes through this fizzing reaction. Okay, now uranium-238, which is another uranium, doesn't do this. It's uranium-235 that does this, not uranium-238, okay? And so there's only one uranium-235 in every 140 atoms of uranium, right? So there's only 1 in 140. So it's not very common. This is what they used to make the first atomic bomb. A little boy that was dropped on Hiroshima. And it took them 2 years to extract enough 235 to make this bomb. 2 years. And the reason is because they are chemically identical. Right? The only difference is that mass. The mass is the only thing that is different. Right? So you can't do any chemical reactions to make them separate apart. Like you couldn't do a reaction and split the 35s from the 238 because they're all going to react the same way. So they had to remove them physically, each atom separately. Now, the way they did this is through gas fusion. Uranium hexafluoride, which is this crazy thing right here, is a gas. And remember this, the larger the gas molecule, the slower it is. Right? Because it's all about kinetic energy, right? And kinetic energy equals 1/2 mv squared, right? Right. So if they have the same amount of kinetic energy, which is just temperature, the one with the larger mass will have a slower velocity, right? And so the smaller gas will move faster. And so they use gas diffusion to split these things apart, right? Gas diffusion. And there's not that much difference, right? It's only 1 uranium in there, so there's not that much difference in speed. So they would have to go through, and if you hear about this on the news when they're talking about other countries making giant centrifuges with their nuclear power plants, this is what they're worried about them doing is separating these uranium atoms apart, and it would enrich or increase the number of uranium-235 atoms. And then when you have an increased number of uranium-235, that's what makes fission, and fission in amounts that could cause explosions happen. And now we're to the next section. All right, so this is called the chain reaction. Now, if you think about this thing, there's 3 extra neutrons that fly apart, right? And if you can get those 3 neutrons to hit 3 more atoms, then you've had 1 reaction cause 3. And then if you have those 3 and the neutrons can hit 3 others, then those 3 will cause 9. And those 9 will cause 27. And those 27 will cause 81. Is that right? Yep. And those 81 will cause 243. And I'm not going to go any higher than that. But this happens very quickly. So this escalates. You have 1 reaction that goes to 3 to 9 to 27 to 81 to 243. All it's just happening in this crazy exponential growth. All right. Oh, I missed a picture over here. Ooh, looky there. So we're having that neutron hit the uranium-235. It's getting excited. It turns into 236.92. And then, poop, splits apart, and there goes the extra neutrons, right? Okay, so that's the chain reaction. Now, if we want to have a self-sustaining chain reaction, that means there has to be enough fissile material for this to occur, right? The neutron will hit one, and this one only has 2 neutrons flying across. But that, I mean, remember, there's different versions. This is just a different version. Okay, simplified version here. So each time we release a little bit of that energy. Remember, we have a little energy. We do whoop, whoop, energy, 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 and so we produce a huge amount of energy because we have all these small reactions occurring very quickly. Okay, now for this to happen, we have to hit the critical mass. In class, I would take a ping pong ball and I would throw it to the large group of people. The larger the group of people, the more likely that ping pong ball, which is representing my neutron, would hit, right? If there's not very many people, chances are the ping pong ball is not going to hit anybody. But if you have a bunch of people all jammed together and you throw a ping pong ball in the middle, it's going to hit somebody, right? And then they'll go throw 3 more ping pong balls each, and their chances are they're going to hit something. So critical mass is the mass needed to sustain the chain reaction. Okay, now let me look at this little picture on this side. Okay, here it is. All right, now the thing we're worried about is neutrons escaping. So if you have a picture A there, there's a small, it may split, it may fizz, right? It may, but for it to go into a chain reaction, the larger that material is, the more uranium you have in there, the greater the chances are it's going to keep going. The neutrons won't escape. I hope that makes sense. Okay. All right, now we have some different names, and these are kind of fun. So we have critical mass, the mass to sustain a chain reaction. And then we have supercritical mass. This is the explosion. This is the uncontrollable, where it goes and produces so much energy they can't keep it under containment. And now we're into talking about the atomic bomb. The first atomic bomb, which was Little Boy, had a size of uranium-235 the size of a baseball. It had a mass of 1 kilogram, and that produced enough energy to equal an explosion from 20,000 tons of TNT. 20,000 tons of TNT. Right? Now, this is how they did it. Now, the hard part of this bomb is real simple design, right? It's real simple. They take 2 pieces of uranium, and those 2 pieces of uranium, this is radium-235, are at subcritical. Subcritical is below critical mass. Subcritical mass, right? And so they have 2 pieces, both subcritical, and then they put some dynamite on the end. And when they want this bomb to explode, they're going to explode the dynamite and shove those 2 pieces of uranium together. Now, they also have some radioactive sources for neutrons in the middle. Now, they wouldn't need if it was 235, I wouldn't think, but this is going to speed up the reaction even faster. All right, and so they jam these 2 pieces together. Now the mass of the uranium becomes above critical mass, up to supercritical mass, and voila, that is the atomic bomb. Very simple design. They knew it would work. They never even tested it before they used it. The test that you see when they do the Trinity test and the one in that's a different kind of bomb. That's a plutonium bomb. They only had enough uranium to make this first bomb, and they didn't even test it. They just thought it was going to work. All right, and so we'll talk about the other one in a little bit. Okay, let's look at the pieces here. So what do they have? 2 smaller pieces, right? 2 smaller pieces are not going to have the chain reaction. They jam them together, and then they have something that is beyond critical. All right. Now, that other bomb. It took them 2 years to get this material for this 235, right? And they didn't want to drop this thing until they had another bomb, right? They didn't want to wait another 2 years. 2 years, oh, here's one, boom, and then wait 2 years and do another. That's a long time to wait. So they had to come up with another design, another idea. And this was the plutonium fission bomb. Okay, now plutonium is, this is plutonium-239. It's a man-made isotope. And the way they make this is in what we're going to call a breeder reactor, and that's coming up in a little bit. So we'll talk about the breeder reactor in a little bit. But they can make plutonium-239 through this little reaction right here. It's a neutron capture. They shoot a neutron into 238. Remember, 238 doesn't fizz. So it joins together and forms uranium-239. But that's not very stable. That's not a natural isotope. And so it breaks down, and I think it said 27 days. Don't quote me on that. But it breaks down and it forms neptunium, which gives off an electron and some other particles there. And then that breaks down and forms plutonium. So what they can do is, by firing a neutron into uranium, it goes through a few cycles, but lo and behold, it becomes this other fissible material. All right, now, it doesn't fizz exactly the same way. It's not the same. So they had to have a whole different kind of system for this. And if you ever watch, it's called The Bomb. It's a PBS documentary. Excellent. It goes through the whole history of the bomb and everything. It is a wonderful documentary. If you got time, if you have nothing else to do, check that out. It's a really good show. And so, okay, that takes care of that picture. All right. So they had to make this new fission bomb, and they made it was Fat Man. Now, this Fat Man was the one they dropped on Nagasaki. Okay, and it was not uranium, but it was the plutonium-235 or 239. Okay, now the whole big thing about Iran last year, right? Or a few years ago, they were talking about, they wanted to have nuclear reactors, and they would check for things, and one of the things they check for is the giant centrifuges, because to make a bomb from a nuclear reactor, you'd have to use a centrifuge, or you'd have to have a breeder reactor. And so we'll talk about those here in this next section. Okay. So, nuclear reactors. Now, a nuclear reactor is a fission based, right? This is the fission section. So, fission, right? And they're going to use either uranium-239, uranium-235, or they can also have a plutonium-239, which we'll talk about that, all right? We'll start off with the core. The core is where the uranium or the fissible material is. Right? And that's where the reaction, the nuclear reaction, is going to occur. All right. But they have to control this thing. They can't have it just go like a bomb, right? It's not going to explode. They don't want that. They want to control this thing. So the way they're going to control this is they're going to use what we call moderators. And moderators slow down the neutrons. Okay, there's a few different moderators. The original one they used for the first reactor was graphite, big blocks of graphite. And graphite's just a form of carbon, the same carbon you use in your pencils, and it slows down the neutrons. All right, so that's made out of carbon. Right. Another one that they use is light water. Now, what light water, and there's heavy water. Light water has just hydrogen. And hydrogen, that means H with 1 proton and 0 neutrons. Okay, so just that's light water, right? So just hydrogen, that's what the water is made out of. And it tends to absorb neutrons. All right, so it's okay at it, but the water absorbs these neutrons, and it kind of, it slows the reaction. Even better than the light water is heavy water. And heavy water has deuterium. And deuterium has hydrogen that has 1 proton and 1 neutron. And so it has deuterium. It weighs more, but it doesn't absorb neutrons as much. So they use heavy water. And it slows down. And when they use the waters, either of these waters, it's going to slow those neutrons down. And so they show these, if you ever see the nuclear reactor, they show it under a big tank of water, like in a big pool. It's like it looks really cool. But but that is to slow down those neutrons. And if they slow those neutrons down, then they won't escape, and it will react and slow the reaction also. Now, we also have what they call control rods. And control rods are materials that absorb neutrons. Right? And so the control rods can be put into the reacting core or taken out. And so if they put them in, it slows the reaction. If they take them out, it speeds it up. And so they can slow down or speed up the reaction just by putting more of these rods in or taking more rods out of the material. And it's just absorbing the neutrons so you can control the level. This gives us back to like Chernobyl and Fukushima, right? The problems in both those situations where they couldn't control the number of neutrons because Chernobyl, the core got so hot that it melted and the control rods wouldn't fit back in. Fukushima, the power went out because of the flood, and they couldn't lower or it knocked out the generators for the electricity, and they couldn't raise or lower the rods, and so they couldn't slow down the reaction. Okay, and so that keeps the reaction between subcritical and supercritical, right? Subcritical means it stops. Supercritical means that it could be explosive, right? Both are bad. You don't want to be subcritical in this case where you have so many fissile materials so close together, because remember, they will produce their own neutrons, right? And if it does start a reaction, because you went too low, you won't be able to control it. And so subcritical and critical and supercritical reactions are not where you want to be. They want to be where they have just the right amount of fission going on. Okay, so let's look at the nuclear reactor. The nuclear reactor, and I'm going to say this, is just a water boiler. Right, that's all. We boil water with it. It makes a tremendous amount of energy, which energy is heat, right? And so they have the reactor here, and look, they're showing the control rods there too. So they have this reactor, and it superheats the water. Okay, now they have a separate system. They have to have a separate system. They can't pump that radioactive water, out into the world. They have to keep that contained. They use that same water over and over. They keep that where it is, but then they have a heat exchanger, right? And so they're going to absorb this heat, and then they're going to use that heat in another tank that's not radioactive water to boil that water in there and turn it to steam and turn a turbine and then turn a generator and then make electricity, right? So when you're at when you see the nuclear power plant up at Lake Erie, they have a huge tower, right? And then they have all that, I always call it the cloud maker, right? They have all that smoke. That's not smoke. That's not radioactive. That's just steam, because this is so hot here. And after it goes through the turbine, there's extra water. That's the cooling tank. And they're trying to cool that water back down so they can use it later. Okay. All right, so that's the basis of a nuclear reactor. All right, now we have a different kind of nuclear reactor. We can have the uranium-235, which is just plain, or we can have the breeder reactor. And breeder reactor, do I have it say it on here? I probably have it. I do. I say it right here. But a breeder reactor, it makes its own fuel. Now, it makes more fuel than it uses. And the way it does is, and we already talked about this in a little bit, they put in a little bit of plutonium-239 and uranium-238. Uranium-238, remember, not fissile. But when that plutonium fizzes, it makes extra neutrons. Those neutrons then, we go through that reaction again, and voila, what do we end up with? More plutonium-239. So when I say we make more fuel, we have to have uranium-238 in there, but it's changing that uranium-238 into a fissile material, and it makes more fuel than it actually uses. And that's almost done here. Now, we're going to talk about the downsides here. We all know what the downsides of nuclear weapons are. We're not going to talk about that right now, but we'll talk about the downside of nuclear reactors. If they use a breeder reactor, they're making materials that can be used in making bombs. Plutonium and uranium are not the same element. So you can chemically separate those. That's why they could separate the plutonium so much quicker than the other ways, because they can use chemical means and separate plutonium and uranium act differently, so they can separate them. Right? Another thing we have to do is we have to store radioactive waste, because there are materials that are made that are still radioactive, and they're poisonous and dangerous to life forms. And there's no place, no one wants to take these. They call it, in environmental science, we call it NIMBA. NIMBY. Not in my backyard. And no one wants to keep it in their own, nobody wants to store this, right? And so this has been a political debate in America for a long, long time. And then we also have the accidents that could occur. If you have a nuclear accident, you're not talking about something that can be cleaned up in a few days, right? Chernobyl is still dangerous, and that's been in 1986. So it takes a long time for these materials to that accidents isn't spelled right. I think I had a spell check on that. All right, but that's it takes a long time for that stuff to get out there, and change. All right. So that's pretty much for the fission section. Remember, you have to answer these, fill out those questions and answer these, or fill out those that notes there. You can type along, whatever. That wasn't that much, right? And then just, type your answers for these. It'd be great too. If you just want to, again, share that, copy that into your Google, and then type out the notes as we go. I know I have pictures that you don't have to draw the pictures. Just type out some definition stuff that we talked about, and then answer these questions, and that will be the rest of this week's homework. Thank you very much, and I hope